In 605 AD, a Chinese engineer named Li Chun finished a bridge over the Jiao River, and modern engineers who studied it in the 20th century said they couldn't fully replicate the construction tolerances using today's tools. It is still standing. It has absorbed 6 major earthquakes, 10 documented floods, and over 1,400 years of foot traffic, cart traffic, and military campaigns. When UNESCO designated it a World Heritage Site, the citation noted that Li Chun accomplished something no one in the Western world would attempt for another 700 years. The question isn't just how he built it. The question is, what did he understand about physics, materials, and failure that we are only now reverse engineering? That bridge is the Jiaozhou Bridge, also called the Anji Bridge, in Hebei Province. And it is the first piece of evidence in a forensic case I want to walk you through. Because what happened at that river crossing in 605 AD was not a lucky accident. It was part of a systematic pattern of engineering intelligence that produced bridges across China for over 2 millennia. Bridges that are still standing, still studied, and in several cases still in use today. Here is the first thing you need to understand about the Jiaozhou Bridge. Every bridge designer in the ancient world built arches one way, semicircular, a full half circle. The Romans did it. The Persians did it. Everyone did it. Because a semicircular arch is intuitively stable. It distributes weight downward in a predictable curve. The problem is that a full semicircle arch is also enormously tall relative to its span. You end up with a bridge that sits so high off the water it requires ramps at both ends, creating gradients that carts and animals struggle to climb. Li Chun rejected the semicircle. He cut the arc. He designed what engineers now call a segmental arch, a curve that covers only 84 degrees of a circle rather than 180. The Jiaozhou Bridge spans 123 feet across the Jiao River, but it rises only 23 feet from abutment to crown. That's a rise-to-span ratio of roughly 1:5. Roman bridges operated at 1:2. The flatter you make an arch, the more it wants to push sideways rather than down, meaning the abutments at each end of the bridge take on enormous horizontal thrust. Li Chun's design pressed outward with forces that would have collapsed any conventional foundation. So what did he do? He spread the abutment load across a wide, shallow stone base embedded deep in the riverbed, not a concentrated point, but a distributed mat of stone almost 30 feet wide. Modern structural analysis confirms the design kept ground pressure at the abutments low enough to sit on the relatively soft riverbed soil without sinking. He calculated this without a single formula. No calculus, no finite element modeling. He worked from empirical trial, generations of builders before him who watched what failed and cataloged why. The knowledge was embedded in craft tradition. Li Chun just pushed it further than anyone had before. But the arch shape was only the beginning. The second innovation is the one that truly separates this bridge from everything built before it. Look at the spandrels, the 2 triangular walls on either side of the main arch between the arch ring and the road deck. In every conventional bridge at the time, those spandrels were solid, filled with stone. Dead weight sitting on top of the arch. Li Chun cut 4 openings into them, 2 smaller arches on each side. Those 4 openings reduce the total weight of the bridge by approximately 700 tons. And the openings do something else, something that becomes critical every time the Jiao River floods. When floodwater rises and begins to push against a solid bridge, it creates tremendous lateral force, what engineers call hydrodynamic pressure. That force has destroyed bridges far more recently than 605 AD. The spandrel openings let the water pass through. The flood doesn't hammer the bridge, it moves through it. Li Chun did not eliminate the problem. He made the bridge permeable to it. Modern structural engineers who published analysis in peer-reviewed journals confirmed that the Jiaozhou Bridge's mechanical behavior corresponds almost exactly to the calculations you would produce today using contemporary bridge engineering science. The stress distribution across the arch ring is nearly uniform. Every segment carries close to equal load. That is not what you get by accident. That is precision. Now the mortar. Because the arch is not monolithic, it is assembled from 28 individual limestone slabs joined together. What holds them is not modern Portland cement. It is a mixture that ancient Chinese builders had been refining since at least the 6th century. A slurry of lime, sand, and the cooked liquid from glutinous rice. Sticky rice mortar. In 2010, a team of researchers at Zhejiang University ran chemical analysis on samples from preserved structures and published their findings. The amylopectin in glutinous rice, the compound that makes the rice sticky, binds with calcium carbonate in lime to produce smaller, more tightly packed calcium carbonate crystals than standard lime mortar creates. The result is a mixture that is more water-resistant, more crack-resistant, and in direct comparison tests, stronger in compression than many formulations of modern Portland cement. Engineers used this mortar recipe in 2019 to restore the 800-year-old Xuchang Bridge in eastern China. It held. The Zhaozhou Bridge is only the beginning. Because the engineering problem the next builders faced was completely different, and their solution required them to think in a dimension the Zhaozhou Bridge never had to. Picture the Dadu River in Sichuan province in 1705. It is not the Jiao River. It is a fast, deep, gorge-carved river running through territory where no stone arch bridge is physically possible. The gorge walls are too steep, the span too wide, the current too violent for any conventional foundation work. Emperor Kangxi needed a permanent crossing. Goods were piling up on both banks because the only way across was a ferry that couldn't always make the crossing. The trade route between Han China and Tibet was effectively severed every time the river ran high. The engineer's solution was iron. 13 parallel iron chains, each one stretching 340 feet across the gorge. 9 chains form the deck, overlaid with wooden planks wide enough for pack animals. 4 chains serve as side rails. The entire structure, all 13 chains, carries a combined weight exceeding 40 tons. The Looting Bridge, completed in 1706, has now stood for over 320 years. What makes the engineering remarkable is not just what was built, it's how. Each iron chain link was forged individually by blacksmiths, stamped with the craftsman's name and weight, and cast to a specified tolerance. The anchor inscriptions on both banks record that Ma Zhichang, a goldsmith from Hanjiang Prefecture, oversaw production. The 12,164 individual iron rings had to be consistent enough in size and strength that when assembled into chains and strung across a raging river gorge, they would carry load evenly. How did they get the chains across the river? The gorge walls did not permit a conventional approach. The most credible historical account holds that the builders first stretched bamboo cables across the river, lighter, more manageable, then used those cables to pull the iron chains across section by section. The anchorage on each bank was a system of iron pillars sunk into stone foundations, with the chain ends bent back and locked through holes in the anchor blocks. The tension of the chains under load presses the anchor system harder into the rock rather than pulling it free. That is a counterintuitive design principle that modern suspension bridge engineers still use. The geometry of the anchor makes tension the mechanism that prevents failure rather than causing it. 320 years later, the Looting Bridge is still crossing the Dadu, still carrying pedestrians. The chains have been periodically maintained, but the anchor system, the fundamental engineering of how that bridge stays up, has not been changed once. Now go further back. Before Li Chun, before iron chains, because the Yellow River posed a problem that neither stone arches nor iron suspension could solve, and Chinese engineers cracked it during the Han Dynasty over 2,000 years ago. The Yellow River at flood stage carries more sediment per cubic foot than almost any river on Earth. The current shifts constantly. Driving permanent foundations into the riverbed is an exercise in futility. The river simply changes course around them or scours the bed out from under them. The Han engineers looked at this problem and concluded that a fixed bridge was the wrong answer. So they built a bridge that moved with the river. Pontoon bridges, a line of boats lashed together with iron chains, a deck laid across them, appear in Chinese records as far back as the 11th century BC, cited in the Zhou dynasty text, the Shi Jing. By the Han dynasty, they were sophisticated permanent infrastructure. The boats were not merely floating. They were anchored with weighted cables to control their position in the current, space to distribute load, and connected with iron chain systems at the deck level to create a surface stable enough for heavy cart traffic. When the river flooded or the current shifted, the sophistication of this approach found its fullest expression in the Guangji Bridge in Chaozhou, first built in 1171 during the Song dynasty. Engineers there confronted a Han River wide enough that no single pontoon system could cross it, but with currents too swift for stone piers in the middle section. Their solution was to combine 3 technologies in a single structure: fixed stone beam bridges on both banks where the water was manageable, and a central floating section of 18 boats connected by iron chains. Boats that could be unfastened during the day to allow large vessels to pass upstream, then repositioned to restore the crossing by night. The world's first opening and closing bridge, built in the 12th century, the Chengyang Wind and Rain Bridge, completed in 1924, though built using techniques refined over centuries, is 64 feet long and contains not a single iron nail. No metal fasteners of any kind. The entire structure is assembled through interlocking timber joints, logs extended out in progressively longer cantilevered layers, each layer supporting the next, the roof structure above locking the whole cantilever array into a unified unit. The weight of the pavilion towers that sit at intervals along the bridge actually stabilizes it, pressing down on the fulcrum points of the cantilever to resist the upward bounce that would otherwise occur when load crosses the mid-span. The 5 pavilions are not decoration. They are structural ballast. Every element that appears aesthetic is performing a mechanical function. In 2019, researchers studying the flood resistance of traditional corridor arch bridges in China published data showing that the woven timber arch bridge typology, another ancient Dong engineering tradition, outperforms modern concrete beam bridges in hydrodynamic load calculations at equivalent span lengths. The ancient design was not just nostalgic. Here is what I keep coming back to when I look at all of this. These engineers had no computers, no CAD software, no standardized material testing, no differential equations. What they had was observation, close, systematic, multi-generational observation of what broke and why. And when a design survived long enough, they understood it had discovered something true about the physical world. Not because it was beautiful, not because it matched a formula, because it was still standing. The Zhaozhou Bridge has now survived 1,400 years. If a bridge built today fails in 50, we ask why. If it fails in 100, it's considered obsolete anyway. We don't even build to the standard of what Li Chun accomplished in 605 AD with hand tools and sticky rice. So here's the question I want you to sit with. We have the computers, the materials, the simulation tools, everything Li Chun didn't have. So why are we studying him? And what does it say about modern engineering that the answer to some of our hardest flood resistance problems might already be sitting in a 1,400-year-old stone arch over the Jiao River in Hebei? Drop that in the comments. I want to know which of these engineering solutions you found most surprising. The open spandrels, the sticky rice mortar, the removable pontoon system, or the nail-free timber cantilevers. Because every one of them solved a specific problem in a way no one was expecting. If this kind of forensic engineering breakdown is what you're into, hit like. It genuinely helps this channel reach more people who want to go deeper than the surface. Share it with someone who thinks ancient engineering means primitive engineering, and subscribe, because next time we're opening up a completely different forgotten system, one that moved water across mountain ranges for centuries before modern hydraulics existed, and that engineers in California are now seriously considering rebuilding.